So today we're carrying on with displacement time graphs. In this section, we will only consider objects moving in straight lines, either right and left or up and down. We're not concerned with 2 dimensions or 3 dimensions. We're just looking in a straight line, also known as linear motion. So linear motion. Velocity can be expressed as a rate of change of position, also referred to as displacement. Displacement over time. So for instance, v is equal to dx dt. That is the derivative of position with respect to time. Acceleration is then another rate of change. So a rate of change of velocity over time. So if we take our v, we get that a is the derivative of v with respect to t. This is also the same as saying the second derivative of x with respect to t twice. Okay, so let's look at example 18. The graph on the right here shows the position x versus time t of a particle traveling horizontally according to the function x of t is equal to t cubed over 2 minus 3t squared plus 4t plus 5, where x is the horizontal distance traveled in meters to the right of the particle's starting point and t is the time in t seconds. So I'll just use some space up here. If this was the particle's starting point, we start timing from when it was 5 meters away from where it started. So that was 5 meters. It's then going to move to 7 meters away, right? So that's around here, or like 6.2, but we're getting pedantic there. It's then going to come back to 4 meters away. So that'll be about there. And then it's going to go back that way forever. So we can see that it's just moving in a straight line. It starts 5 meters away in terms of where we're timing, and then it goes a little bit further, then comes back, then keeps going on forever to the right. So we're asked, in what direction did the particle move initially? So when we started timing, which direction was it going? Well, it was starting at 5, and then it went towards 7. So it's going towards the right. We're then asked to calculate the average velocity of the particle over the first 2 seconds. So if we've got 2 seconds there and our initial time at t equals 0, what is our average velocity here? Well, this is a rather imprecise diagram. So rather than using interpolation and following this up to try and get what is the actual value, we're going to substitute t equals 2 into our initial equation. So this can be expressed as average rate of change, average velocity, let's say. Actually, I'm going to get rid of that entirely and just call it v average. So that's going to equal the distance at 2 minus the distance at 0 over 2 take 0. So the distance at 2, we've got 2 cubed over 2, that's 2 squared, 4, minus 3 times 2 squared, that's 12, so 4 minus 12, plus 8 is going to get us 0, and so we're going to get 5 minus 5 over 2 minus 0, which gives us 0 over 2, which is 0 meters per second. So the average velocity of the particle over the first 2 seconds is 0 meters per second. And this is where the idea of average velocity is quite weak, because we know that it's been moving, but just by looking at these 2 points, we can see, or we think, that the average velocity is 0. It's not moving. So this is why we use instantaneous velocity to help clear out things like this. Okay, part C. Determine the speed and acceleration at which the particle was traveling after 3 seconds. So we need to find v of 3 and a of 3. Well, let's first derive x of t, which is going to give us v of t, which in this case will be 3t squared on 2 minus 6t plus 4. And then our second derivative is going to be 3t minus 6. So we can see that v of 3 is going to be 3 times 9 on 2 minus 6 times 3 plus 4. Well, that's going to give us 27 on 2 minus 18 plus 4. I'm going to have to use a calculator for this one. That gives us negative 0.5. What's our units? Meters per second. So meters per second. Some will see this written as ms to the negative 1. Both are acceptable. Then we also have a of 3, which is going to be 3 times 3 minus 6, which is 9 minus 6, which is 3 meters per second squared, or meters per second to the negative 2. Okay, so that is everything that example 18 was asking for there. And you can hear there's the bell going. So we've got these examples here, 13.2 and 13.3, and we're looking at those questions for this lesson. Thank you.